Okay, let's take a look at the energy of a satellite in orbit. So this satellite here obviously has an orbital radius, which we're going to assume we know, and it also has an orbital speed or an orbital velocity. That's the velocity that's keeping it in orbit. So the energy of this satellite is just the sum of those two energies. It has kinetic energy due to its speed, and it has potential energy due to its position above the Earth. And the total energy of this satellite, we know kinetic energy is 1/2 mv squared, and the potential energy is a negative energy, so minus g m1 m2 over r. And the important thing to note about the velocity or the speed of this object is we know that it has speed because the Earth's gravitational pull is creating a centripetal force. And what happens is one of the r's cancels, the mass of the satellite cancels, and what we have is an equation just for v squared. It's g times m over r. Well, we can take that and plug it into this equation up here, and now our total energy becomes 1/2 times g times m1 times m2 over r minus g times m1 times m2 over r. So the total energy here is just negative 1/2 times g times m1 times m2 over r. So this equation here doesn't appear on the formula sheet, so you're going to have to derive it. You can't start from this point, but hopefully now you understand where it comes from, so you can derive it on a test. But it tells us the total energy of the satellite, and the only piece of information we need to know about the satellite, other than the mass of the satellite and the mass of the object it's orbiting, is its orbital radius. And we can find its total energy. Note that it's still negative, right? And again, it's negative because the satellite is still trapped in the Earth's gravitational well. Okay, so it still has a negative amount of energy, right? The potential energy, which is negative, is still larger in magnitude than the kinetic energy, which is positive. So you end up with a negative amount of energy. Okay, the other types of questions you'll often be asked is how much energy does it take to take the satellite and move it into orbit? So obviously to move it in orbit, we need to change its position. So we need to have a change in the gravitational potential energy, but we also have to have a change in the kinetic energy. Okay? So again, that requires us to do work, right? And that work will equal the change in energy. So that work can either be the change in just the potential energy, so you can find out how much work does it require to lift the object up to this height, or you can find the change in the total energy using the equation that we just used. And again, that one is going to require you to look at just the orbital radius, right? So the final being the final radius in orbit, and then we're going to subtract, sorry, this would be a negative, subtract the initial energy, which is the initial radius, which will just be the radius of the Earth. Right? So once we take care of all of the negative signs here, what we have is 1/2 times g times m1 times m2 times 1 over the initial radius minus 1 over the final. Right? So I factored out the common elements, took care of the negative signs so that I have a nice, neat formula. So again, this now tells me the amount of energy I need to go from one orbit to another orbit. But again, read questions carefully, because sometimes they may only ask you how much energy to take an object from here to here. In that case, all we're looking at is the change in the potential energy, right? Which would be negative g m1 m2 over r final minus g m1 m2 over r initial. Right? This is a very different equation than the one we have up here. Right? It's about half. Okay? So these two things are calculating two different quantities. This is to be in orbit, right? So it includes the kinetic energy. This equation is just the change in height. Okay, so we know the satellite still has a negative amount of energy, but another quantity that you might be asked to find is what is the escape velocity? Okay, so instead of going to orbit, what if I actually wanted to escape from the Earth's gravitational pull? Well, in order to escape from the Earth's gravitational pull, we need to have a positive amount of energy. So the total energy has to be greater than or equal to 0. Okay. So the total energy, we're going to set it equal to 0 to find the minimum amount. And so the total energy is going to be the kinetic plus the potential. And we know that the kinetic energy, 1/2 mv squared, and the potential energy is g m1 m2 over r. So I've taken care of the negative signs here. The mass of the satellite disappears. And what we get is v is equal to 2 times g times m2 over r. And this is what's called escape velocity. Okay. So this is the minimum speed that this object needs in order to escape from the Earth. Okay. If it doesn't reach this speed, eventually it's just going to end up in some orbit way, way, way far out, and it's not going to escape from the Earth. So this is known as escape velocity, and it occurs when the total energy is 0. So in other words, the kinetic and the potential are exactly equal to each other. Okay. All right, so that's energy and satellites. Hopefully that makes sense, and if not, you can track me down in class.